This class, we're going to look at graphing the transformations of y equals sine of x. We've already looked at the basic function for y equals sine x and y equals cos x. And the transformations, we're going to use just sine x in this lesson, but all of the transformations work exactly the same for the cosine function. So it's really helpful if you've got a graphing calculator handy for this. And let's review where the window settings should be. Okay, so if you press your window button, we're going to have the calculator set up in degrees. And again, just even though we're doing this in degrees, it works exactly the same if we're working in radians. And we'll do some of those together in class, practicing with radians. So we're going on along our x-axis from negative 180 to positive 720 degrees with an x scale of 90. The y minimum, let's switch that to negative 5 to positive 5. Just so that we have a little bit more range available to us. And let's put in the sine function, so sine of x. And if you click on that little symbol next to the y1, you should be able to change what the line looks like that's used for that. This one doesn't want to cooperate with me that way. But you could change it to a dotted line. But if we hit graph, we see there's the sine function. Remember, it starts at 0 and does one full cycle or period in 360 degrees. So to the right of the y-axis there, we see two full periods as we go from 0 to 720 degrees. So the function we're going to graph is y equals 2 times the sine of x. And you might want to think about what that's going to look like. If you leave the y equals sine of x in y1 for each example, and we'll only add in the new one, it's very easy to compare the old one with the new one. So we'll go 2 times sine of x. And let's hit graph and see what we see. So the new graph has been stretched. It now goes, the highest point is at positive 2, the lowest point's at negative 2. So if we look now at what has changed, okay, we now have a mapping rule that says that xy maps onto our x's all stayed the same. Horizontally, nothing changed on that graph, but the y values were all doubled. Okay, so the mapping rule will be xy maps onto x and 2y. And so I've redone the original table of values here. Our new table of values, the x's will stay the same, but our y values are doubled. So they'll go 0, 2, 0, negative 2, and 0. And you'll see if you look back at your graph on the calculator, you'll see that that is the case. Okay? So in general, when we have a number a multiplied by sine x, it gives us a vertical stretch of a. So for instance, if I did y equals 1/2 sine of x, I'll just bring the calculator up and we'll do that one. If I go to y equals, and instead of sine x, do 1/2. There's the original y equals sine x. And here's the new one, y equals half sine x. And you can see that it's half as high, so a vertical stretch of 1/2 in that case. So if you think of the characteristics of a sinusoidal function or of the sine curve itself that we looked at in the previous lesson, we talked about amplitude, period, domain and range, etc., the vertical stretch affects our range, okay? And also the amplitude of the curve. So when we're talking about range, we're talking about the specific y values that the function covers. When we talk about amplitude, we're talking about the distance from the sinusoidal axis, from the middle of the curve to its peak or to its low point. So the vertical stretch affects those two. It doesn't change the period or the sinusoidal axis, but just range and amplitude. So let's move on to the next transformation, and that is a reflection in the x-axis. So if we look at the equation I've put here, I've put a negative in front and I've said 3 sine x. This 3 is like an A, is going to give us that vertical stretch. It's the negative in front that's going to give us the reflection in the x-axis. So let's go to the calculators. Again, leaving sine of x as the first equation, and we'll put in negative 3 sine x for our second equation. So negative 3 times the sine of x. Hit graph. Let's see what happens. There's y equals sine x. And here comes the negative 3x. Notice the vertical stretch. Our peaks and valleys are higher. And the graph has flipped so that in the original one where we went above the x-axis, now we're going down below. So again, the amplitude has been changed because of the vertical stretch, and it's been reflected down, reflected in the x-axis. The sinusoidal axis is still the same. It's still the x-axis. The period is still 360 degrees. The domain is still all real values for x. So let's look at the mapping rule. XY maps onto our x's stayed the same, but our y's are multiplied by negative 3. Okay, so there's our original part of the table of values. Here's the new one. If we multiply by negative 3, and if you think about how that graph went, we started at 0, went to negative 3, back up to 0, up to positive 3, and then back down to 0 in one period. So a reflection by itself, doesn't change the amplitude, doesn't change the sinusoidal axis or anything. It only reflects the graph in the x-axis. Okay. All right, let's look at vertical translations. So we'll look at 2, and based on your experience of vertical translations, if we take the sine of x and add 2 or subtract 3, hopefully you've got a good idea of what's going to happen there. So let's again go back to the calculator. Let's leave sine of x as our original equation there, and let's have the sine of x plus 2 as our second equation, okay? In this case, it's really important that you close the bracket after the x. So let's hit graph and see what happens to the graph. There's our original y equals the sine of x, and now we're adding 2 to it. Notice that the size and shape of the graph has not changed at all. The only thing that's changed is that the whole thing has shifted up 2 units. It's still exactly the same size. The period is the same. The amplitude is the same. What has changed is the range of the function, and what has changed is the sinusoidal axis, because the sinusoidal axis, the line, the horizontal line that it runs through it, is now at y equals 2. So if we go to our mapping rules, we could say for this one that xy maps onto x and y plus 2. And if we do y equals a sine of x minus 3, we could put that one on the same graph. It'll look kind of nice if we do. If we go to y equals 3 or y3 equals and enter sine x, close the bracket, subtract 3, and hit graph. You can see the whole graph has shifted down 3, but it's still the same size. Okay, so give yourself a little quiz now and decide which of these features or characteristics of the graph has changed. Okay, our sinusoidal axis has gone up 2 in the first case, or down 3, so it became, let me rephrase that, the sinusoidal axis became y equals 2, or in the second case, y equals negative 3. That's giving it as the equation of the line for the sinusoidal axis. The period, it stayed the same. The actual amplitude of the function stayed the same as well. The curve, those curves still have an amplitude of 1 because it only goes up and down 1 unit from the sinusoidal axis. The domain also stayed the same. All real values, all real numbers are valid for x. However, the range did change. In the first case of y equals sine of x plus 2, notice that the lowest value was at 1 and the highest value was at 3. And in the second case where we subtracted 3, our highest value was negative 2 and our lowest value was negative 4. Okay, so the range and the sinusoidal axis changed with the vertical translation. And I see I didn't write the mapping rule for the second one here, but it would be x and y minus 3. Okay, so you're just adding 2 to the y's in this case, subtracting 3 from the y values in that case. All right, let's start looking at the horizontal transformations. And a horizontal translation, when we're talking sinusoidal functions, a horizontal translation is actually called a phase shift, and your textbook uses that term all the time. And so, but it works exactly the same as the horizontal translations in the other functions that we've studied so far. So I've got y equals the sine of x plus 45, and y equals the sine of x minus 90. We'll only do these one at a time as we look at them. So let's go back to the calculators and leave only our original equation in. And again, double check that your calculator's in degrees here, but we want to do the sine of x plus 45. And before you hit graph, you might want to make a prediction to yourself as to where that graph has gone. So when I hit graph, here's our original one again. And here's the new one. You'll notice that it has shifted left by half of a tick mark, and the tick marks we set up to be every 90 degrees. So it's actually shifted left 45 degrees. Okay, so the horizontal translation is left 45. Okay, so our mapping rule then becomes xy maps onto x minus 45 and y. So instead of our original of 0, 90, etc., we're actually starting at negative 45. And then still going up by 9 as we're subtracting 45 from each of our values. But our y values stay the same, so 0, 1, 0, negative 1, and 0. Okay, and that was that first graph. So adding 45 degrees within the function here shifted us left 45 degrees. So make your prediction for the second example here of y equals a sine of x minus 90. And let's open up the calculators and graph that one. So we'll leave our first one the same, and we'll put in the sine of x minus 90. And see what that looks like. Now, because it's periodic, it's tough to tell because it actually looks like it could have gone left 90 or right 90. And that's because of, well, actually not left 90, but left 270. And that's because of the periodic nature of sinusoidal functions. Okay, you could say, well, it's shifted right 90 or it's shifted left 270. But we're going to call it shifting it right 90. Okay, so I'm going to just minimize that a second. So our xy maps onto x plus 90 and y. So our new table of values then starts at 90, and we're adding 90 to each of the values. And we go up to 450. And if you check your graph, you'll see that this is true, that at 90 degrees, we're at 0, at 180, we're 1, etc. So the phase shift, if you think of the characteristics of the sinusoidal curves, if you think of the characteristics, does it affect the amplitude? Does it affect the period? Does it affect your domain and range, etc.? The phase shift only affects where the cycle starts, or where you're starting the cycle at 0. However, it does not change the sinusoidal axis, domain, or range, or amplitude or period. Okay? So it affects the start of the cycle it doesn't affect domain, range, amplitude, period, or sinusoidal axis. Okay, one more transformation to look at, and that's our horizontal stretch. We'll do that by looking at these two examples. One is where I'm multiplying the x by 2, and another one where I'm multiplying it by 1/3. And if you recall how horizontal stretches work, you might want to make a prediction as to what the horizontal stretch is equal to for these, and think about what characteristic of the function it might change, and what might our new mapping rule for these two functions look like. Excuse me. So let's go to our graph and enter in that new function for our second function. So sine of 2x. And let's hit graph. Okay, if you look at what happened there, the new graph, the new cycle goes much quicker. In the time of one cycle from 0 to 360 degrees, it's actually gone twice instead of just once. Okay, so it's actually compressed or shrunk the graph. We have a horizontal stretch of 1/2. It's only half as wide as it was. And our mapping rule then becomes xy maps onto 1/2 x, and y stays the same. So if you think of our original values for x, our new ones are going to be half of that. So 0, 45, 90, 135, and 180. But our y values stay the same, 0, 1, 0, -1, and 0. Okay, so make your predictions for our second example here. And let's put it in and confirm those predictions, okay? So if we go to y equals, oh, so I go to y equals and put in now the sign of 1/3 x. There's my original one again. Notice that we haven't took the whole distance across, including the negative side of the x-axis, to actually get us through one complete um, cycle of the curve there. So if you predicted that you would have a horizontal stretch of 3, or the reciprocal of the 1/3 there, you'd be correct. So our mapping rule will be that xy maps onto 3x and y. So our x values have all been multiplied by 3. So that will give us 0, 270, 540, 810, and I forget that one, I don't have it at the top of my head, 1080. And our y values 0, 1, 0, -1, and 0. Okay, so if you think about the horizontal stretch and what it affects, it doesn't change domain or range or sinusoidal axis or amplitude. It only affects the period. Okay, and it affects the period by the reciprocal. So when x is multiplied by 2, the period is half of its original amount. So it's really, the period becomes 360 divided by whatever that letter was. Let's say it's b, if b was the number in front of the x. It's 360 is multiplied by the reciprocal. So it would also be 2 pi divided by b. So in the first case, it would be 2 pi divided by 2, or in the second case, 2 pi divided by 1/3, which would make it 6 pi as the period. Okay? And you can see the period by looking at this, because our tables of values are set up to give us one full period of one full cycle or one full period of the graph. So you can see that by looking at this chart, that you can see what the period is. It's always going to be the difference between our first value and our last value. Okay, so that is the 5 different transformations. In our next class, we'll look at putting them all together and do a lot of practicing of putting them together and how we can do more than one at the same time.